Hello and welcome back to the class of 5G. Previously, we talked about how 2G transitioned from analog to digital and how it was ready to cater more consumers than ever. In this lecture, we will talk about what is cellular approach of communication and how it plays a vital role in the success of both 2G and digital. Let's say we have some geographical area, and we are talking about relatively large area which houses at least more than one mobile phone towers. Say we have tower 1 and tower 2 and both are operating at the same frequency, which is F1. If that is the case, then their frequencies will turn out to be noise for each other, and they might even end up cancelling each other's signals out, and that's not what we want. So we need to make sure that if there are two towers nearby, they communicate on different frequencies. If tower 1 is using frequency F1, tower 2 should use something like F2, which doesn't have to be higher or lower in particular, it just have to be different from F1. Now if we take this same problem on a larger scale in a bigger geographical area, there are chances that many towers will try to use the same frequency and end up clashing with each other. To resolve this issue, almost hexagonal pieces of geographical areas are marked as a cell, and the whole area is divided into multiple cells, which creates a cluster of cells. In other words, the same geographical area, which was considered as a whole, is now considered as a cluster of different cells, and each cell houses a base station or a mobile tower. The logic behind this is pretty much simple. If one cell in a cluster is using frequency F, then no other cell within the same cluster can use the same frequency. Since the cluster will be made of 7 hexagons, there needs to be 7 different frequency bands allotted to them. But why hexagon? You see, it's about geometry. Try to divide the geographical area into circles. When you do so, you miss out on two important parts. One, the outer boundary of the circle, and two, the intersections of the circle. So the consumers traveling through or residing on those missing out parts of the geographical area would be difficult to handle, because then the towers will be confused about which users to cater and which not to. Similarly, if we take square, it is difficult to cover an abstract area using squares. You will miss out a lot due to the edges. Hexagons is the closest you can get to cover the full area of an abstract shape. And so, entire regions, I'm talking about cities, states, countries, were divided into hundreds and thousands of different hexagons to act as the housing of the towers or base stations. It also made frequency allocation pretty much easier, because just like allotting different frequencies is important, making the frequencies reusable is also important. The spectrum is limited. In other words, we can't just go around allotting random frequencies to random antennas. That's not how it works. We need to make sure that we can reuse the frequencies as much as possible to cater as many consumers as possible within the band available to a service provider. Cellular approach made it easier than ever. We mentioned that a cluster cannot have repeated frequencies, but it also means that outside the cluster, the frequencies can be reused again. And if we have a standard pattern for that, we can make sure, at least on paper, that frequencies won't clash with each other. For example, check out these dark blue hexagons. They can share the same frequency without interfering with each other. And the process to map them is also pretty simple. Take one cell, allot it a frequency, say F1, move two cells straight and one cell adjacent, and the same frequency can be reused. So the ground for frequency allocation was set. Next challenge was how to utilize the allotted frequency as efficiently as possible within a cell. And to address that, we will take a look at what is multiple access in the next lecture. Till then, happy learning, and I hope you have a nice day.